The story begins not with a flash of light, but with its opposite, a silence. It is a quietude that settled over the Space Telescope Science Institute in Baltimore, a palpable stillness born not of inactivity, but of a sudden, profound interruption in the steady stream of photons and data that had flowed, like a cosmic heartbeat, for over 3 decades. The Hubble Space Telescope had gone blind. Its eyes, those polished mirrors and exquisite sensors trained on the deepest fields of the universe, had closed. But in the echoing silence that followed the failure, a different kind of observation began. Engineers and scientists, their hands hovering over keyboards in dimly lit control rooms, began to look backward, not into space, but into time, into the final, precious cache of observations Hubble had completed just before the safe mode engulfed it, a data package transmitted home in the last clear moment before the signal faded. They called it the Final Downlink, a routine term for an extraordinary archive, the last undisturbed vision of the cosmos from a living legend. What they found within that dataset was not merely a collection of pretty pictures. It was a sequence of observations that told a story Hubble itself was never designed to see. A narrative written in the faintest glimmers of ancient light that seemed to contain a discrepancy, a subtle anomaly buried in the noise, a whisper of something that, according to our most fundamental maps of cosmic history, should not have been there. This is the account of what Hubble saw in its final clear moments, the vision that arrived just before the data vanished into the void of a system's failure, a vision that challenged our understanding of the universe's first chapters. To understand the weight of this final glimpse, one must first appreciate the nature of Hubble's gaze. It is not a sudden, piercing look, but a slow, patient accumulation of photons, each one a messenger from an almost unimaginable distance. For the targets in question, a seemingly blank patch of sky in the constellation of Fornax, adjacent to the famous Hubble Ultra Deep Field, the telescope had been commanded to stare not for hours, but for over 100 orbits of the Earth. Its Wide Field Camera 3, a workhorse instrument installed during the final servicing mission, was configured in a very specific way. Its infrared channel was tuned to catch the faintest, most redshifted light that had been stretched by the expanding fabric of the universe during an epic journey of over 13 billion years. This was not astronomy of the present. It was archaeology of the dawn of time. Each pixel in the resulting image represented a monumental act of collection, gathering the sporadic, tired photons from galaxies so young they were little more than infant sparkles of fusion in the primordial dark. The program, known officially as a Deep Legacy Survey, was one of hundreds in Hubble's queue, remarkable only for its depth and its chosen coordinates. A place deliberately selected for its cosmic emptiness, a clean window into the deep past. The data downlink proceeded with the mundane efficiency of 1,000 such transfers before it. Bits streamed through the tracking and data relay satellites, down to White Sands and across the continent to Baltimore, where they were automatically processed, calibrated, and added to the pipeline. The initial, automated reductions revealed the expected, a deep, grainy field, speckled with thousands of faint, red smudges, proto-galaxies from the epoch of reionization, seen as they were when the universe was less than 5% of its current age. It was a magnificent image, a testament to Hubble's enduring power. But then, the failure. An aging gyroscope sent erroneous readings. The spacecraft's protective software tripped, and the great eye closed, turning away from the universe to stare inward at its own faulty systems. In that moment of crisis, the newly arrived data took on a different character. It was no longer just another dataset. It was potentially the last deep field image of an era. The scientific team, led by a quietly determined astrophysicist from the University of Cambridge, who had spent her career modeling the first galaxies, began a more painstaking manual analysis. They were looking for the expected, the luminosity functions, the star formation rates, the clustering properties of these infant structures. But as they applied sophisticated filters to isolate the very highest redshift candidates, the very first objects to emerge from the cosmic dark ages, one region of the image refused to conform to their models. There, in a quadrant comprising just a few arcseconds of sky, was an overdensity, not of bright, obvious galaxies, but of a particular type of ultraviolet emission, a signature known as Lyman-alpha. This spectral line, a fingerprint of hydrogen gas being excited by hot young stars, is the primary tool for detecting the universe's first stellar populations. But in this patch, the Lyman-alpha signal was both stronger and more extended than any simulation predicted for such an early time. It manifested not as a discrete blob from a single galaxy, but as a faint, nebulous glow, a kind of luminous fog spanning a region that, at that redshift, corresponded to several thousand light-years across. According to the canonical timeline, the universe at this epoch, roughly 500 million years after the Big Bang, was still a largely neutral, opaque place. The first stars and galaxies were only just beginning to pierce the primordial hydrogen fog, their fierce ultraviolet radiation slowly carving out transparent bubbles around them in a process called reionization. This particular glow, however, suggested a bubble of such immense size and advanced development that it seemed to imply a coordinated, widespread episode of star formation that began earlier and proceeded faster than our best cosmological models allowed. It was as if Hubble had caught a glimpse of a cosmic metropolis under construction far sooner than the blueprints of the universe permitted, its streetlights already blazing in what should have been the deepest part of the cosmic night. The initial reaction within the team was not excitement, but a profound and careful skepticism, a disciplinary instinct honed by decades of chasing phantoms in the noisy data of the deep sky. The luminous fog in the infrared data that extended Lyman-alpha halo could be an artifact. It could be the subtle, cumulative effect of stray light from a much closer, brighter galaxy just outside the frame, its photons scattered by Hubble's own optics in a way the calibration routines had failed to fully subtract. It could be an unexpected interaction of cosmic rays with the camera's detectors, leaving a faint, persistent echo in the exact same pixels over multiple orbits. Or, most pernicious of all, it could be a statistical fluke, a chance alignment of noise that, to the human eye yearning for pattern, coalesced into the illusion of a signal. The lead astrophysicist, Dr. Alara Vance, whose career had been built on computationally simulating the universe's first billion years, knew the weight of extraordinary claims. She immediately halted the broader discussion and directed her small team into a mode of forensic data audit. They would attack the finding from every conceivable angle, not to prove it, but to dismantle it. They reprocessed the raw data from scratch, using different algorithms and more aggressive noise filtering techniques. They modeled the point spread function of nearby bright stars with exquisite care, subtracting any possible contribution of their light. They consulted with the instrument team at Goddard, examining the telemetry logs from Wide Field Camera 3 for any anomalies in voltage, temperature, or detector behavior during those specific orbits. For weeks, the glow persisted. It was not a sharp feature, but a gentle gradient, a contour of excess brightness that survived every test of systematic error, a ghost in the machine that refused to be exorcised. This left the more intriguing, yet formidable, possibility that the signal was real, but not from the epoch it appeared to be. The entire enterprise of deep field astronomy hinges on the accurate measurement of redshift, the stretching of light's wavelength caused by the expansion of the universe. A high redshift signifies a great distance and an early time. The candidate region's redshift was estimated through a technique called photometric redshift, inferred from the object's brightness through several different colored filters. It is a powerful method, but not infallible. Could this be a lower redshift galaxy, perhaps a dusty, star-forming system from a much later cosmic era, masquerading as a primordial one? Its light, reddened not by cosmic expansion but by vast internal clouds of dust, could slip through the filters and mimic the signature of an extremely distant object. Dr. Vance's team embarked on a spectral analysis of the faint glow, using every trick in the Hubble archive to tease out a spectral line, a definitive fingerprint that would pin down its distance. The data was at the very limit of Hubble's capability, a whisper at the edge of hearing. They applied Bayesian statistical models, running millions of simulations to compare the observed flux with templates of galaxies at various redshifts and of various types. The result was consistent, yet frustratingly probabilistic. The object was most likely at an exceptionally high redshift, but the confidence intervals were wider than anyone liked. The Lyman-alpha feature itself, while seemingly present, was blurred, diffuse, lacking the sharp peak that would make its identification unequivocal. This ambiguity was, in itself, a clue. In the modern local universe, Lyman-alpha emission is typically absorbed by the interstellar and intergalactic medium. When we see it, it is usually a clear, narrow line from a galactic core. In the early universe, however, the physics is messier. The escaping radiation from the first stars must navigate a thick, clumpy, neutral hydrogen fog, which can scatter the Lyman-alpha photons, reddening them and stretching their emission into a broader, shallower profile. The very diffuseness and redness of the signal, the characteristic that made it so hard to pin down, was also a hallmark of the theoretical predictions for light escaping from the reionization epoch. It was at this juncture, with the team mired in methodological uncertainty, that they turned to a different archive, the legacy of Hubble's own past. The coordinates of this mysterious field had not been chosen at random. They lay in a strategic void next to the Ultra Deep Field, a region that Hubble, over its long life, had observed many times, with different instruments, in different wavelengths, and for different purposes. Dr. Vance had the idea to search for any earlier, shallower glance at the same patch of sky, a glance that might have been too brief to reveal the faint glow, but which could now serve as a crucial cross-check. They found it in data from over a decade prior, from the now decommissioned advanced camera for surveys. In that older image, a single short exposure in a specific optical filter showed a barely there smudge, a hint of something that had been flagged by an automated processing pipeline years ago and dismissed as likely noise or a cosmic ray hit, for it had no counterpart in the other filters taken at that time. No one had pursued it. Why would they? It was one faint anomaly among thousands in a shallow survey. But now, with the deep infrared data providing a context of profound depth, that forgotten smudge aligned perfectly with the heart of the extended Lyman-alpha glow. Hubble had seen a whisper of this object over 10 years earlier, a fleeting, marginal note in its own long diary, a note whose significance only became clear when read alongside the final, deep entry written just before the systems failed. This was the moment the investigation shifted. The convergence of two independent datasets, separated by a decade and collected by different Hubble instruments, transformed the signal from a maybe into a something. The object was not an artifact of a single camera's quirks on a specific day. It was a persistent feature of the cosmos, a feature whose light had been traveling for over 13 billion years, patiently waiting for its story to be assembled from fragments of data across the telescope's lifetime. The scientific narrative now began to crystallize around a compelling, if unsettling, hypothesis. Hubble's final deep view, combined with this archival whisper, suggested the telescope had captured evidence of a protocluster in the act of formation, but at a time far earlier than such vast structures were thought to assemble. A protocluster is the embryonic stage of a galaxy cluster, the largest gravitationally bound structures in the universe, containing thousands of galaxies, vast clouds of hot gas, and immense quantities of dark matter. In the modern cosmos, they are the metropolises of space. Our models of structure formation, which are exquisitely successful at predicting the large-scale cosmic web we see today, paint a picture of a bottom-up hierarchy. Small things form first, then merge under gravity to become larger things. The first stars ignite in small dark matter halos. These gather into protogalaxies. Protogalaxies then slowly draw together over billions of years to form clusters. The luminous, extended emission Hubble saw suggested something different. It hinted at a region where star formation was not occurring in isolated, brilliant knots, but was instead widespread across a vast volume of space, as if 100 nascent galaxies had all switched on within a relatively short cosmological window, their combined ultraviolet output creating a giant, ionized bubble in the neutral hydrogen. This implied that the underlying dark matter skeleton, the invisible gravitational scaffold upon which all visible structure is built, had already collapsed into a massive, complex web at a startlingly early epoch. The universe, it seemed, might have gotten a faster start than we imagined, with the seeds of its greatest structures planted and already sprouting in the first few 100 million years after the Big Bang. This was the quiet, profound tension embedded in the data that arrived just before the vanishment, a vision of premature cosmic maturity, a challenge to the serene, gradual timeline of our standard model of cosmology, written in the faintest possible light from the edge of time itself. Confronted with this persistent signal, this whisper of premature structure, the team's work transitioned from data forensics to cosmological interpretation, a shift that required them to step back from the pixels on their screens and contemplate the vast, mechanistic engine of the universe's expansion and growth. The standard model of cosmology, known as lambda cold dark matter, is a breathtakingly successful narrative that describes the evolution of the cosmos from a hot, dense plasma to the intricate cosmic web of galaxies and voids we observe today. Its parameters are finely tuned by a symphony of evidence: the cosmic microwave background radiation, the large-scale distribution of galaxies, the accelerating expansion driven by dark energy. Within this model, the formation of structure is a stately, hierarchical dance dictated by gravity, acting on the invisible substrate of dark matter. Small perturbations in the primordial density field, imprinted by quantum fluctuations in the universe's first inflationary instant, grow slowly over cosmic time, eventually collapsing to form the first stars and galaxies hundreds of millions of years after the Big Bang. The existence of a vast ionized bubble and a coordinated burst of star formation at a redshift of approximately 12, as Hubble's final data hinted, would not shatter this model, but it would strain it, pushing its mechanisms into a regime of unexpected efficiency and speed. It would suggest that the initial density fluctuations in that particular region of space were anomalously high, or that the physics of gas cooling and star formation in those first halos was more potent than our simulations accounted for, or perhaps that some other, more obscure process was at work, injecting energy and triggering collapse ahead of schedule. To test these ideas, Dr. Vance initiated a collaboration with a group of computational cosmologists at the University of California, Santa Cruz, specialists in running immense, physics-rich simulations of the universe's early epochs. They took the precise coordinates, the estimated redshift, and the photometric properties of Hubble's mysterious glow and used them as a constraint within their simulation suite, a virtual universe called ASTRAL, which modeled the interplay of dark matter, gas dynamics, radiation, and chemistry, from the Dark Ages through the epoch of reionization. The question they posed to the simulation was blunt. In a universe governed by our standard lambda CDM rules, how likely is it to form a structure with the observed luminosity, physical extent, and ionized bubble size at this specific cosmic time? The initial results were sobering. In the vast volume of the simulated universe, a cube billions of light years on a side structures of such maturity and coordination at zeta 12 were exceedingly rare, appearing in fewer than 1% of all analogous volumes. The simulation could produce them, but only in regions where the initial random roll of the cosmic dice had produced a massive, concentrated overdensity of dark matter, a peak in the primordial density field that stood several sigma above the average. This was possible, but statistically unlikely. More intriguingly, when the simulators isolated these rare, early-forming protoclusters in their virtual cosmos and studied their subsequent evolution, they found that such a head start had profound downstream consequences. By the time the universe was half its current age, these regions had snowballed into the most massive galaxy clusters in the entire simulation. Behemoths that contained hundreds of trillions of stars and sat at the nexus of gigantic filaments of the cosmic web. Hubble's Final Deep Field, therefore, might not have just captured an early anomaly. It might have captured the infancy of one of the most titanic structures in the modern universe, a cosmic monarch in its cradle. This probabilistic framing, a possible but unlikely fluctuation, was scientifically comfortable, a safe harbor within the existing paradigm. Yet, there remained a nagging detail in the Hubble data that resisted even this explanation. The extended Lyman-alpha emission was not symmetric. The careful surface brightness maps, painstakingly constructed from subtracting every conceivable background, revealed a morphology that was subtly elongated and included what appeared to be faint, filamentary tendrils connecting the central glow to several of the fainter, point-like proto-galaxies in the vicinity. This was no simple spherical bubble. It looked like a network, a nascent cosmic web in miniature, with the ionizing radiation from the first stars seemingly tracing the pathways along which gas and the invisible dark matter that guided it was flowing into the growing structure. This filamentary morphology was a predicted signature of the so-called cold flow accretion model, where pristine hydrogen gas from the intergalactic medium streams along dark matter filaments directly into the centers of growing galaxies, fueling rapid star formation without first being heated to extreme temperatures. To see evidence of this process, which simulation predicted, but which had never been conclusively observed at such an early epoch, was breathtaking. It meant Hubble was not just seeing a collection of early objects. It was witnessing the dynamic, gravitational anatomy of structure birth itself, the luminous tracer of a hidden, dark matter skeleton that was already complex and well developed when the universe was in its infancy. This detail moved the observation from a statistical curiosity to a direct, phenomenological probe of the fundamental process of cosmic construction, offering a real-world glimpse of a mechanism previously only viewed in the abstract realm of supercomputer visualizations. The implications of this began to ripple outward, touching on one of the most profound puzzles in modern cosmology: the nature of the first sources of light that ended the cosmic dark ages. The epoch of reionization, when ultraviolet radiation from these first stars and galaxies broke apart the neutral hydrogen atoms that filled the universe, is a pivotal, yet poorly understood chapter. When did it start? How long did it take? Was it driven by a vast population of small, faint galaxies, or by rarer, brighter objects? Hubble's potential protocluster presented a scenario where reionization could have been a highly inhomogeneous and patchy process. Instead of a uniform, rising tide of ionizing photons, the universe might have been pierced first in specific, overheated regions like this one, where an early concentration of star formation created giant, overlapping ionized bubbles. These bubbles would then have expanded over hundreds of millions of years, eventually merging to complete the process. If such powerful early engines were more common than our simulations suggested, they could have provided a significant fraction of the photons needed for reionization, shifting the burden away from the uncounted legions of tiny, unseen galaxies. This would, in turn, solve observational tensions between estimates of the total ionizing photon budget and the actual number of early galaxies we can detect. Hubble's last deep view, therefore, was not just a picture of a place. It was a potential key to a timing problem that defines our understanding of the universe's transition from a simple, opaque state to the transparent, complex cosmos we inhabit today. The data that arrived before the vanishment held within its grainy pixels a clue to how the lights first came on, and why they came on when they did, a narrative written in the ionization state of hydrogen atoms that have long since been incorporated into stars, planets, and perhaps life. As the analysis deepened, the team confronted a more terrestrial, yet equally complex dimension of their discovery: the intricate and fragile chain of custody that brings starlight from the edge of the universe to a scientist's workstation. Hubble's data does not arrive as a finished image, a pristine portrait of the deep sky. It arrives as a torrent of ones and zeros, a raw digital record of photon counts, voltages, and timestamps, heavily encoded and compressed, bearing the minute scars of its journey through space, its processing by onboard computers, its relay through communication satellites, and its final reconstruction on the ground. Every dataset is a palimpsest, with the faint cosmic signal written over a substrate of instrumental signatures and systemic noise. To trust the anomalous glow, they had to understand, at an even deeper level, the instrument that had captured it in its final moments of clear vision. Wide-field camera 3, Hubble's workhorse since 2009, is a masterpiece of optical engineering, but it is not a perfect, static eye. Its detectors age. Their sensitivity to different wavelengths changes imperceptibly over time due to constant bombardment by cosmic rays. The thermal environment of the telescope fluctuates as it passes in and out of Earth's shadow, causing minute expansions and contractions in its optics. All of these effects are meticulously calibrated out by pipelines that reference vast libraries of ground tests and in-flight monitoring data. But could there have been a subtle, uncharacterized shift in the camera's behavior in the days or hours leading up to the safing event that took Hubble offline? The team delved into the engineering telemetry, the heartbeat of the telescope, searching for any correlation between the anomalous glow on the sky and an anomalous flicker in the voltage of a power supply, or a tiny, transient spike in the temperature of the infrared detector. They found nothing conclusive, only the normal, gentle sawtooth patterns of the telescope's orbital thermal cycle. This absence of evidence was both reassuring and unnerving, for it left the signal standing alone, its reality hinging purely on the statistical weight of the photons themselves. It was during this meticulous review of housekeeping data that a junior researcher on the team, specializing in data transmission protocols, noticed a minor anomaly unrelated to the camera itself, but tied to the very act of the data's delivery. The final downlink of the deep field observations had occurred across multiple passes via the Tracking and Data Relay satellite system. Each pass, a brief window of communication. As Hubble arced over a ground station, packages of data were transmitted, received, and acknowledged. In the log files, one of these transfer packets, corresponding to a specific segment of the infrared exposures that covered part of the mysterious glow, showed a slightly higher than usual rate of correctable errors. These were not dropouts or data loss. The onboard error, correcting codes, had worked perfectly, reconstructing the bit stream exactly as sent. But the increased error rate suggested a noisier transmission link at that moment, perhaps due to a passing solar flare adding static to the radio band, or a minor misalignment in the satellite relay. This was a routine occurrence, and the data itself was certified as intact. Yet, in the hyper-vigilant atmosphere of the investigation, it introduced a seed of metaphysical doubt. Could the very process of transmission, the journey of the data across 340 miles of space and thousands more across the ground, have left some imprint? The idea was far-fetched, a shadow of paranoia, but it underscored the profound truth of their endeavor. They were not studying the ancient universe directly. They were studying a digital reconstruction of it, a representation mediated by technology, vulnerable to a chain of contingencies that stretched from the telescope's gyroscopes to the amplifiers in New Mexico. The signal's journey from a primordial hydrogen cloud to a graph on a Baltimore screen was a miracle of engineering, And like all miracles, it was fragile. This fragility became part of the story's tension, the possibility that the whisper from the dawn of time had been subtly altered, not by cosmic processes, but by a ripple in the radio waves between the stars and the Earth. This period of instrumental introspection coincided with the most challenging phase of the scientific process, preparing the findings for submission to a peer-reviewed journal. Dr. Vance insisted on a paper that was a masterpiece of caution, presenting the data in excruciating detail, outlining every test performed to rule out artifacts, and foregrounding the multiple alternative explanations that remained viable. The central claim would not be, "We have discovered an impossibly early protocluster." It would be, "Hubble has observed an extended Lyman-alpha emission region at Z12 with properties that are statistically unusual in the context of standard hierarchical structure formation models." The difference in phrasing was the difference between hype and science, between a headline and a contribution to the long, slow conversation of cosmology. The draft paper included the archival whisper from the Advanced Camera for Surveys, the results from the ASTRAL simulations, showing the rarity of such objects, and the tantalizing filamentary morphology. It also included a full section on the transmission error anomaly, dismissing its relevance to the scientific content but documenting it transparently. The paper's tone was dry, technical, and heavy with caveats. Yet between its lines, any expert reader could feel the tremor of excitement, the hint of a paradigm being gently stressed. They titled it neutrally, "An extended Ly-alpha emission region at Z is approximately equal to 12 inches the Hubble parallel field. Constraints on early structure formation." The act of writing it, of forcing the ethereal mystery into the rigid format of an Apj manuscript, was a grounding ritual. It transformed the experience from one of wonder into one of argument, building a bridge of logic and evidence from the raw pixels to a conclusion that could be debated, challenged, and hopefully accepted by the community. Before submission, however, came the internal review, a gathering where the entire team and selected outside experts pored over every sentence and figure in a marathon session. It was here that the most profound philosophical question emerged, posed by an elderly cosmologist invited for his skeptical mind. He pointed not to the data, but to the act of observation itself. "We are discussing," he said, his voice calm but insistent, "the statistical likelihood of this structure existing based on our models of the entire visible universe. But we must remember that Hubble, in its entire lifetime, only observed a minute fraction of the sky. This deep field is a pinprick, a straw drawn from a cosmic ocean. What if we have, by sheer chance, drawn the one straw that contains the most extreme, earliest forming structure in our entire cosmological volume? What if this is not evidence against our models, but a lesson in the fallacy of small number statistics? We build theories from the average, but the universe always presents us with the specific." His point was a cold splash of humility. The anomaly's very existence could be a selection effect, a consequence of the fact that our most powerful telescopes spend thousands of hours staring at a few, supposedly representative, blank spots. If you look long and deep enough at any one place, you will eventually find something that appears to break the rules, simply because the rules are written for the ensemble, not the individual. This was a possibility they could not disprove. It meant that the ultimate meaning of Hubble's final glimpse might not be resolved by Hubble at all. It would require a larger survey, a statistical census of many such deep fields, to see if early, extended emission regions were truly rare anomalies, or merely the first of a new, unseen population. That census would require a telescope with Hubble's sharpness, but a far larger field of view and more sensitive infrared eyes. It would require, in other words, the James Webb Space Telescope. The submission of the paper to the Astrophysical Journal marked not an end, but a beginning of a new kind of waiting, a suspended state where the delicate finding existed only within the minds of the authors and a handful of anonymous referees, a secret held in trust by the rigorous but fallible institution of peer review. In this interim, the Hubble telescope itself remained in safe mode, a slumbering giant orbiting silently in the perpetual night, its last clear vision now a subject of intense study on the planet below. The team dispersed to their other duties, but a shared, unspoken tension remained. They had sent a message in a bottle into the academic ocean, a bottle containing a map to a place that might not exist, drawn from the last light before a silence. Dr. Vance found her thoughts returning, not to the complex statistical arguments of the paper, but to the raw, simple beauty of the image itself. On nights when the weight of ambiguity grew heavy, she would call up the final, processed field on her large monitor, turn off the overhead lights, and just look. The thousands of galaxies, each a smudge of light representing billions of stars, formed a tapestry of staggering depth. And there, in one quiet corner, was the subtle, ethereal glow, a faint, amorphous cloud of pale crimson against the black. It did not shout. It did not dazzle. It was a barely there sigh in the visual data, a region where the emptiness of space seemed just a little less empty, a little more textured with ancient energy. To the untrained eye, it would be invisible, a patch of slightly grainy background. To her, it was a window. She contemplated the physical reality it represented, a region of space several thousand light years across, over 13 billion years ago, filled with the searing ultraviolet light of countless first-generation stars, stars that lived fast and died violently in supernovae, seeding the pristine gas with the first heavy elements, the carbon, oxygen, and iron that would one day form planets and life. That glow was the nursery of everything that came after in that entire region of the cosmos. It was a founding moment, and Hubble had captured its fading echo just before its own voice was temporarily stilled. While the scientific process marched on, a parallel narrative began to unfold in the engineering centers dedicated to Hubble's health. The failure that triggered the safe mode was traced to a specific gyroscope, one of the remaining three that were critical for the telescope's precise pointing. The gyro was providing erratic readings, forcing the spacecraft's computer to assume it was tumbling, and thus shut down non-essential systems to safeguard its solar panels and optics. The engineering teams at Goddard and the Space Telescope Science Institute began the delicate process of devising a recovery plan. Could the faulty gyro be coaxed back to stable operation? Could Hubble operate on 2 gyros? Or even 1, with new software algorithms to compensate? These discussions were technical, filled with acronyms and telemetry codes, but their subtext was profoundly human. The struggle to extend the life of a beloved machine to regain its gaze. Every command sent uplink was a risk, a potential to worsen the situation. Every day in safe mode was a day of lost science, a day the universe went unobserved by one of its most patient witnesses. This engineering drama lent a poignant, retrospective gravity to the final deep field dataset. It was no longer merely the last observation of a cycle. It had become, potentially, the last deep observation of Hubble's entire career, if the recovery efforts failed. This unspoken possibility added an elegiac layer to the analysis. The data gained a historical weight, like the final diary entry of an explorer lost in a vast wilderness. The team's work was now not just about understanding the early universe, but about curating and interpreting one of the final, complete gifts from a legendary instrument. The pressure to be right, to be meticulous, to honor the data was immense. The first response from the journal's referees arrived after 8 weeks. It was a classic, thorough peer review, skeptical, demanding, and immensely valuable. The referees did not reject the paper, but they raised pointed questions that cut to the heart of the findings' fragility. One referee focused on the photometric redshift estimate, demanding a more sophisticated analysis that would quantify the probability that the emission was actually from a lower redshift dusty interloper. Another zeroed in on the potential for circumgalactic emission from from a slightly lower redshift galaxy just outside the field to be scattered into it, creating the illusion of an extended, high redshift halo. A third questioned the statistical significance of the filamentary structures, suggesting they were consistent with random noise patterns at such low signal-to-noise levels. The requests were fair, the challenges precisely targeted. The team regrouped, not with disappointment, but with a sense of purpose. This was the process working as it should, sanding down the rough edges of a claim, testing it against the collective wisdom and skepticism of the field. For 2 more months, they performed the additional analyses. They ran a battery of new spectral energy distribution fitting models using a wider library of galaxy templates, including extreme dusty starbursts at intermediate redshifts. They performed detailed point spread function deconvolution on all nearby bright sources to model their scattering wings with unprecedented accuracy. They applied random field simulations to calculate the likelihood that noise could conspire to produce the apparent connecting filaments. The supplemental work was grueling, a deep dive back into the granular details of pixels and error bars. Yet, with each test, the core finding, while diminished in certainty, held. The probability of a low redshift interloper was reduced to a few percent. The scattering from known nearby galaxies was insufficient by a factor of 10 to explain the glow's surface brightness. The filamentary patterns remained statistically unlikely to be pure noise, though their confidence was lowered. The revised paper, now 50 pages longer with appendices, was resubmitted. It was a stronger, more defensible, and more humble document. The anomaly was now framed even more cautiously, not as a challenge to cosmology, but as an interesting stress test of its predictions at the very highest redshifts. During this period of revision, news came from the engineering teams that was both a relief and a harbinger of a new era. After a series of cautious procedures, they had successfully revived Hubble. They had managed to stabilize the errant gyro by employing a little-used operational mode that involved cycling its power and letting it rotate at different speeds, essentially jogging it back to health. The great telescope was awakening, its systems coming back online, its aperture door reopening to the stars. The astronomical community breathed a collective sigh of relief. But the recovery also marked a turning point. Hubble was back, but it was an aging observatory. Its future, while extended, was now clearly finite. Every new observation would be a bonus, a precious extension of its legacy. And this context made the pre-failure deep field all the more significant. It was a reminder of what Hubble, at the peak of its capabilities, could still achieve. It was a benchmark against which its future observations and the observations of its successor would be measured. The return to operations also meant that, in principle, Hubble could now be pointed back at the same field. It could take more data, go even deeper, or use its spectrographs to attempt to secure the definitive redshift measurement that would lock in the distance of the mysterious glow. A proposal was hastily drafted and submitted for directors' discretionary time, arguing for urgent spectroscopic follow-up. But the observing schedule was a crowded river, and the telescope's time was the most sought-after resource in astronomy. The proposal entered a queue, its fate uncertain. The universe, having offered one enigmatic glimpse, seemed to withdraw, leaving the question hanging in the silent space between the stars. A question now awaiting not just the verdict of peer review, but the possibility of a second look from an awakened, yet aging, sentinel. The universe, in its infinite patience, operates on timescales that dwarf human endeavor, yet it occasionally permits a convergence, a fleeting alignment, where opportunity and curiosity meet. For the team awaiting the final verdict on their paper and the decision on their follow-up proposal, this convergence arrived not from Hubble, but from a mountain peak in Chile. The Atacama Large Millimeter, Submillimeter, Array, ALMA, a vast interferometer of radio dishes that sees the universe in the light of cold gas and dust, had been conducting its own deep field surveys in regions overlapping with famous Hubble fields. A separate team, investigating the cold gas content of galaxies in the early universe, had inadvertently captured the same patch of sky where Hubble's enigmatic glow resided. ALMA does not see starlight or ionized hydrogen. It sees the faint millimeter-wave emission from cosmic dust grains warmed by starlight and the specific spectral lines of molecules like carbon monoxide. The ALMA data, released to a public archive, was like a photograph taken in a completely different spectrum, revealing a hidden layer of reality. When Dr. Vance's team cross-matched the coordinates, they found, to their stunned silence, a faint but distinct detection. ALMA saw a cloud, not of ionized hydrogen, but of cold, dusty gas, precisely co-located with the heart of Hubble's extended Lyman-alpha emission. The implications were profound and paradoxical. At such an early cosmic epoch, the universe was thought to be pristine, largely devoid of the heavy elements needed to form dust. Dust is forged in the furnaces of evolved stars and scattered by their explosive deaths. Its presence implies that not only had the first generation of stars in this region already lived and died, but that a second generation of stars had already formed from their enriched ashes. This was a staggering acceleration of the cosmic life cycle. Hubble's glow showed a region lit up by intense, ongoing star formation. ALMA's whisper revealed that this was not the first act, but likely the second or even third, that this protocluster was not a newborn but a precocious toddler, its environment already polluted with the soot of its deceased stellar predecessors. The two independent observations, from two utterly different telescopes operating in different physical regimes, created a stereo image of the early universe, and the picture it painted was one of startlingly rapid maturation. This discovery forced a radical recalibration of the theoretical models. The ASTRAL simulations were rerun with new parameters, allowing for extremely efficient metal production and rapid recycling of gas within these early overdensities. The updated models showed that if the dark matter halo collapsed early enough and was massive enough, it could pull in vast reservoirs of pristine gas with such violence that the first star formation would be explosive and brief, leading to prompt supernovae that would quickly seed the surrounding cloud with metals. This enriched gas, cooler and more prone to fragmentation, would then collapse to form a second wave of stars more efficiently, creating a starburst that could produce both the observed Lyman-alpha luminosity and the detectable dust emission. The timeline was breathtakingly compact. All of this first stars, their deaths, enrichment, and a second major burst of star formation had to occur within the first 500 million years of the universe. It was a scenario that pushed the physics of galaxy formation to its limits, demanding extreme efficiencies and densities. Yet, the concordance of the Hubble and ALMA data made it the most plausible narrative. The early universe, it seemed, could have pockets of intense, accelerated evolution, like patches of alpine flowers that bloom violently in a brief summer, while the rest of the cosmic landscape still lay under the snow of the Dark Ages. This finding transcended the specific anomaly. It provided a potential mechanism for how the most massive clusters in the present-day universe got their head start. They weren't just born in slightly denser regions. They were born in regions that operated on a fast-forwarded clock, where the stellar life cycle spun at a frenetic pace, building up a dense, rich environment eons before their more sedate counterparts. With this powerful multi-wavelength confirmation, the revised paper sailed through the next round of peer review and was accepted for publication. Its release into the world was a quiet event in the broader media landscape, but within the cosmological community, it sent a subtle tremor. Here was not a definitive discovery announced with fanfare, but a deeply documented, cautiously worded case study that presented a puzzle. The paper's very restraint gave it weight. Colleagues began to re-examine other deep Hubble fields, looking with fresh eyes for similar extended, high redshift emission. Theorists began to incorporate the possibility of such fast-track overdensities into their models of reionization, exploring whether a smaller number of these intense regions could be as important as a vast sea of tiny galaxies in burning off the hydrogen fog.